Okay, in this video we'll take a look at the whole idea of conservation of energy, but we'll look at it when friction is acting in the system also. And this creates a little bit of a problem because what friction basically does is takes energy that would normally be in the system and would stay in the system and removes it. So friction, as we've talked about, friction generally creates a lot of heat, and that heat is then just released to the air, and so then it escapes the system, the car or the skateboard or whatever the object that that normally would have been holding on to all of its energy. So we've looked at situations where the potential and the kinetic, or some combination of potential and kinetic, was transformed, but the energy all stayed in the system. And so when friction acts on the system, it creates a little bit of a problem because technically some of the energy is leaving the system, but as long as you account for that energy, as long as you take into consideration that energy, you can still figure out things like how fast or how far or what was the force that was acting on an object. And so we're just going to take a look at the same kind of conservation problems. We're just going to add one new layer, and that is to add the friction. So obviously friction always does negative work, because friction by definition always opposes the motion of the object, or the displacement of the object. So if the object is displaced to the right, then the frictional force always acts to the left, and one of those two guys has to be negative. So no matter what, friction is always going to produce this negative work. It always takes away from the total energy that's available from the object. So we'll take a look at an example problem and just see how can you approach this, like what can you do to take care of this. And I would like to solve this problem in two ways. So first I'm going to solve the problem without friction, just to show you that there is something not right. And then we'll address the frictional force, and we'll be able to actually calculate the frictional force. And so I'll show you two ways that you could do that. So in this example problem, we'll have a skateboard with no person on it. The skateboard is going to be allowed to roll down a hill that is 6 meters high and 10 meters long. And when the skateboard reaches the bottom, it is found that it is only moving at 8 meters per second. And so that means you'll see that when we calculate without friction, that it should be going faster. The skateboard should be traveling faster, but it's only traveling at 8 meters per second, and so therefore some energy must have been lost, and that energy must be accounted for in terms of friction. So before we actually try to solve the problem, let's just draw a simple picture. So the height of this thing is 6 meters, and the length is 10. And what we learned through the concept of conservation of energy is that it doesn't really matter how long this is. I can have a very steep ramp or I can have a very shallow ramp. It doesn't really make a difference. All I really need to know in terms of conservation of energy is how high, right? Because gravity does not do any work horizontally. Gravity only does work vertically. So all we really needed to know was the vertical height. So if there is no friction, we'll look at that example first. Then this problem is pretty simple. We start at the top of the hill with the skateboard, and the skateboard is going to roll down the hill, and when it reaches the bottom, the skateboard is going to have some velocity. Okay, and we can very easily calculate what the velocity of that thing will be by just simply recognizing that the potential energy at the top must be equal to the kinetic energy that we have at the bottom. And we've done this problem many times, so we'll just go quickly through this. So mgh is equal to 1/2 mv squared. Obviously in this case we really don't need to know what the mass of the skateboard is, and we would find that v is equal to the square root of 2 times g times h. And we'll just throw another equal sign over on the other side, and we'll go ahead and plug the numbers in. So that's 2 times 10, and it was said that the hill was 6 meters high. And so we'll calculate the answer for this guy. So this is the square root of 2 times 10 times 60. I don't know why I said 60. That doesn't make sense. square root of 2 times 10 times 6. And we find that the velocity should be about 11. So in the absence of friction, what we should find is that the velocity of the skateboard at the bottom is 11. But when we get to the bottom, we find that it's only 8. So that means that there is some missing or some unaccounted for energy. So the way that I would suggest that we would approach it, there's two ways you could think about it. So first of all, the potential energy that we have at the top, we won't get all of it. So one way to approach it would be to say the following. We could say that EP, right? But we're not going to get all of that potential energy, so we need to subtract out the work due to friction. So the total amount of energy is not going to be EP, it's going to be EP but minus whatever frictional energy is present in that system, and that's energy that is always going to be in the form of work. And then that leftover energy, whatever is left over, that will be transformed into kinetic energy. Right? But obviously, another way of thinking about it is that the potential energy that it has at the top, by the time it gets to the bottom, that energy will have been transformed into two different forms. And so what we might say is that EP was transformed into kinetic plus the work that was done by friction. And it should be pretty obvious that this is the same equation. It's just different ways of thinking about it. I can subtract the work that was done from the initial amount of energy that I had, or conversely, I could just say that this potential energy was transformed into two different kinds of energy. One is the kinetic energy at the bottom of the ramp, and the other one is whatever work was done by friction. I'm going to continue on with the right side over here, and you'll see that in this case, plus F of F times D. Now, because the frictional force does not depend directly on the mass, we're not using coefficient of friction, which would actually bring the mass in, but because right now I don't know the coefficient of friction, I will not be able to cancel the masses out. This is super important. Right? Back in the previous problem, we were able to cancel out the masses, and it really didn't make a difference, but now it does matter. It does matter what the mass of this is. I cannot just cancel out the masses if all I am looking for is the frictional force. So in this case, probably what will be the easiest way for us to approach this one is we'll just go ahead and plug the numbers in, and then we'll move everything over to one side. So this is a mass of 1.2 times 10 times 6 meters equal to 1/2 1.2 times the velocity, and we were told that the velocity, just to go back here, that at the bottom the velocity was 8. Plus F of F, which I don't know, but I do know the distance. Now this is really important to notice. The distance is not the 6. So the frictional force is not acting vertically. The frictional force acts parallel to this surface. So the distance that the frictional force acts on is not 6, but it's actually 10. So the friction acts all along this plane, and it was told that that thing was 10. Okay, so just putting together the numbers. So 1.2 times 10 times 6 is 72. That's equal to 0.5 times 1.2 times 8 squared. That is 38.4 plus, and I'm just going to reverse the order of this, plus 10 times F of F. Okay, so just a couple algebraic steps to get to the final answer, and that is we're going to subtract the 38 from the other side. That would give me 33.6 equal to 10 F of F. And finally, the frictional force is going to be 33.6 divided by 10, which would be 3.36 newtons. Now we could have alternatively done something a little bit different, is At the bottom, we had a kinetic energy that corresponded to 8 meters per second, but we should have had a kinetic energy that corresponded to 11 meters per second. So what I might have tried to do was to look at the difference in kinetic energy from what I should have had compared to what I did have, and that of course represents missing energy. And what is the name of that missing energy? The work done from friction. So I could have looked at the difference and realized what I'm not saying the change in kinetic energy. I'm saying the difference between what I should have had compared to what I actually got, and that would have actually allowed me to calculate the amount of work in essentially a third different method. Personally, I feel like this is the way that I tend to like to set up the problem. Whenever there is work done by friction, I just make sure to add it in. I just add in that work, and just make sure that it gets accounted for either by subtracting it from the initial total energy, or just tacking on to the end as another form of energy that's going to exist at the end of the problem. That form of energy is something that will show up later at the end of the problem. So that's one example of how you might use this idea of friction and the work that is done by friction to solve a problem that's a little more realistic, because in the real world the friction is almost always there. So let's give you a second example, going back to a sort of a simple problem, something that we've looked at this problem before, but just putting a kind of a new twist on it. So we'll get rid of this one, and in our second example, we're going to have a 1,200 kilogram car accelerate from a green light by producing a thrust force of 7,800 newtons, but the car also experiences an average drag force of 2,100 newtons. And what we're being asked to do is to determine how fast the car will be traveling after it's gone 50 meters. So in this problem, the old way of doing it, let me just show you how we would have done it in the old way. The old way would say to do this. And we'll do the new way over here on the right. So the first thing that what we would have done is we would have said that F net equals MA, and that is equal to, and I have two forces. There is the thrust, and there is the drag force. Okay, and I have both of those, plus I have the mass. So that means that the acceleration of the car would be the thrust minus the drag divided by m, and that is equal to 7,800 minus 2,100, all divided by 1,250. So that would let us get the acceleration of the car, and that is going to be, so we're going to end up with 5,700 divided by 1,250. Oh, cannot operate this calculator. 5,700 divided by 1,250, and that would give us an acceleration of 4.56 meters per second squared. Okay, and then in the second step, then we would go back to the old kinematic equations. So I have A. I also know that the initial velocity was 0, and I know that the displacement was 50 meters. So if I wanted to know V, if I wanted to know the final velocity, I would just use the old kinematic equation, which says that V squared is equal to V naught squared plus 2AD. I would get rid of this since the initial velocity is 0, and I would find that V is equal to the square root of 2 times 4.56 times 50, and that gives me a velocity of 2 times 4.56 times 50, 21.4. 21.4 meters per second. Okay, so that's the old way of doing things that we've done in the past is we used combinations of the net force combined with the old kinematic equations. And this combination of net force with this equation was very common in the problems that we looked at. So in the new way, and the new way is using energy, we would want to set up an equation that addresses the kinds of energy. So obviously the thrust force is doing work, no question about that, but also the drag force is doing work, and the drag force is taking away from the total work that we have available to us. So I would think of it this way. I would say W net. So the net amount of work, I have some positive work, but I also have some negative work, and that will be equal to my delta EK. Okay, so there are actually two different works happening over here on the left, so I'm going to go ahead and put those both in. So that would be W thrust, but minus the W from the drag force, and that would be equal to 1/2 mv squared minus 1/2 mv naught squared. Okay, but obviously this is 0, so we can just get rid of that. And I have all of these numbers, so the work from the thrust force would be equal to F of T times D minus F of D times the displacement, and that would be equal to 1/2 mv squared. Now we could do the algebra, so we certainly could just solve for V right now. It's kind of a big mess, the equation, so probably I'm sure you would prefer to just go ahead and start plugging the numbers in right now. So we have 7,800 times 50 minus 2,100 times 50. Okay, so that's going to give me the total work that was done. The positive work from the thrust, subtract out the work that we lose from the drag force, and again, that'll mostly be turned into heat and also maybe a little bit of sound, and that will be equal to 1/2 1250 times V squared. So on the right side we end up with 625 V squared equal to 7,800 times 50 minus 2,100 times 50, and that is 285,000. Okay, now the engine's producing more work than this, but this is all we're going to get because we have to take out the part that was lost to the friction. So if we just take that number and now divide by 625, that tells us that V squared is equal to 456, and therefore V is equal to the square root of that, and that is 21.4 meters per second. So there's really no advantage of one method over the other. It's just two different approaches. These are the two big approaches to solving problems in mechanics. You either take a force approach or you take an energy approach. And one of those two will generally allow you to solve, and usually you can do it by both methods. In fact, almost every case you could do it by both the energy approach or you could do it by the force approach, and it just depends on which way you find easier. Right now we're in the section on energy, and so you would be expected on a quiz to be able to show that you can use an energy approach to solve the problems, but technically almost every problem that can be solved by the energy approach could also be solved by just using the old force equations combined with kinematic equations. Technically I did this with one equation, so it was in a sense some ways simpler, but you can see obviously it was quite a complicated equation. I had to take a lot of things into consideration, but in the end I produced the same answer, 21.4. So that's how you deal with friction. You just treat it as another form of energy that you have to take into account, and you just make sure that you add it in correctly.